Hello? Hi, everybody. I would like to welcome you all to this evening's lecture. My name is Eleni Ornell, and I am the chair of the mathematics department here at Stanford. Tonight's lecture is jointly organized and sponsored by the Stanford Mathematics Research Center and the Stanford Institute for Theoretical Physics. This lecture is also part of a series of public lectures, roughly about 2 per year, which are organized by the Stanford Mathematics Department and sponsored by the Stanford Mathematical Research Center and the Friends of Stanford Mathematics. If you would like to be notified about future events like this, but you are not on our mailing list, please send me an email at chair@math.stanford.edu. This evening, we are very fortunate to have as our speaker Professor Robbert Dijkgraaf. Before we begin, let me just tell you briefly a few things about our speaker. Born and educated in Netherlands, Professor Dijkgraaf obtained his bachelor's, master's, and PhD degrees in theoretical physics from Utrecht University. Since 2012, he has been the Leon Levy Professor and the director of the Institute for Advanced Study in Princeton. He is a mathematical physicist who has made significant contributions to string theory and also to the advancement of science education. Professor Dijkgraaf is also the president of the Inter-Academy Partnership since 2014, a past president of the Royal Netherlands Academy of Arts and Sciences, and the distinguished public policy advisor and advocate for science and the arts. His research focuses on the interface between mathematics and particle physics. In addition to finding surprising and deep connections between matrix models, topological string theory, and supersymmetric quantum field theory, Professor Dijkgraaf developed precise formulas for counting of bound states that explain the entropy of certain kinds of black holes. For his contributions to science, Professor Dijkgraaf has received the Spinoza Prize in 2003, the highest scientific award in the Netherlands. And in 2012, he was named a Knight of the Order of the Netherlands Lion. He is also a member of the American Academy of Arts and Sciences and of the American Philosophical Society. Professor Dijkgraaf is also a trained artist, writer, and popular lecturer. His annual televised lectures on science attract more than 1.5 million viewers in the Netherlands. And he also writes a monthly column for Holland's top newspaper, NRC Handelsblad. Most recently, Robbert wrote a companion essay to the classic 1939 essay, The Usefulness of Useless Knowledge, by the Institute of the Advanced Studies founding director, Abraham Flexner. It provides a modern argument for supporting the curiosity-driven basic research and original thought that are critically important for future innovation and societal progress. So we are really delighted to have Robbert with us tonight. His title is Quantum Mathematics and the Fate of Space, Time, and Matter. So please join me in welcoming Professor Dijkgraaf.
Thank you so much for this very kind invitation. What a pleasure to see all of you here, in particular my dear friends and colleagues, both of mathematics and physics. So I'm kind of perfectly happy to talk about the interaction of the two. And I want to begin by saying some words about the role of mathematics vis-a-vis the natural sciences. So one point is that mathematics, which of course strives for kind of eternal truth, it's also very much an environmental science. But it's this famous line by, I think it's from Jean-Pierre Serre, that said that physicists try to find out which laws God picked for the universe. Mathematicians try to find out which laws even God has to obey. And, but on the other hand, many of the concepts we use in physics, in mathematics, have in some sense natural sources. So, and there were wonderful quotes of this. This is the famous quote of Galileo. He spoke about the book of nature. The book of nature that if you cannot understand it, you are wandering around in a dark labyrinth. So the natural language in which kind of physics or science is written is mathematics. This was true in the 17th century, but there are some kind of more modern advocates of that point of view. Here's Richard Feynman, by the way, not known as a great connoisseur of refined mathematics, but yet he says, for those who do not know mathematics, it's difficult to get across a real feeling as to the beauty, the deepest beauty of nature. If you want to learn about nature, you have to learn the language that she speaks in. On the other hand, another quote of him says that if all mathematics disappeared today, physics would be set back exactly 1 week. Now, don't applaud too soon, because this might be a very smart remark, till I actually had a very famous mathematician giving the perfect answer to this. That was the week that God created the world. So I would say math, physics 2-1 as an intermediate score. But the question is, of course, so how are mathematical concepts illuminated by the world? And I want to bring him into a wonderful essay actually written by the late Bill Thurston. He wrote, a famous mathematician, of course, certainly well known here in this area, essentially describing what is the best definition of a mathematical object. And he took something that we all kind of know, the derivative of a function. So how do you describe the derivative of a function? And he basically says the following. He said, well, we can start with like the technical formal definition with epsilon and delta, and very tellingly in the article he has it wrong. But then his point is, well, we can also think of this as the rate, the velocity. And if you don't know that, then you know actually it can also be a vector. It can have a certain direction. You can think of a function in a higher dimensional space. Well, it can be the tangent. It can be tangent plane, so immediately you understand functions of more than one variable. Well, definition 4 is infinitesimal, with infinitesimal variations. Or think about discrete variations. Or think about symbolic manipulation of derivatives. Or the linear approximation, or the microscopic view. You zoom in into the function. And he goes on and on and on, and certainly this definition 37, which is some particular Lagrangian section of a cotangent bundle, very technical definition, but at some point he needed definition 37. But his main point is we need all of them. You are in a very, very poor position if you cannot kind of enjoy all these different perspectives. So in some sense, a good mathematical subject has, like a diamond, has many different facets that illuminate itself. Now, another point I want to bring with you, that there is some very important symbol in mathematical equations. So typical mathematical equation looks like this. I want to point out a kind of forgotten symbol, which is in the middle. It's the equal sign. And I know philosophers sometimes talk about this as kind of what they call Clinton's principle. That's really a 1990s concept. But there was a definition on what the meaning of is. What do we mean exactly if you create A and B? But it's wonderful that some of the most beautiful equations in mathematics, they connect two different worlds. So I think very appropriate, the equal sign is these double lines, because in some sense I would say intellectual ideas can flow from A to B and from B to A. And sometimes these connections are really surprising. Some of the most elegant equations in physics have the property too. One great master of that was Einstein. Now, perhaps equals mc squared is the most famous equation in the world. But of course, before Einstein, E and m, energy and mass, were totally unrelated concepts. Just the fact that you find both of these elements in one equation was incredibly powerful. Of course, it tells you that you can, if you move, you will be a little bit more massive, and you can take mass and convert it in pure energy. So I think many of the equations have this property, and actually that's what basically will be the overarching theme today in my lecture, how mathematics can connect different worlds and what we learn for it. So you will see many examples which are like Rosetta stones, where there are two different languages that in some sense find a dictionary. If math is the natural language of the physical world, we'll see that the physical world doesn't have yet a universal language. There are various kind of dialects, languages that have to be connected. In fact, if you look in mathematics as a pure technical thing, you can see some of the large developments in modern mathematics. I'm listed here a few will feature in my lecture, but for instance, the Langlands program, a very famous, or the whole studying of number theory and geometry, that are these wonderful equations that are somehow marrying two worlds that some said nobody thought would actually meet. In physics, perhaps the most famous example is the duality that arises in the early days of quantum mechanics. You know, the Heisenberg's uncertainty principle, the fact that an electron or any other object could be both a wave and a particle. So my favorite line for this is actually from Werner Heisenberg. So when, from Wolfgang Pauli. Heisenberg makes the discovery, writes it to his good friend Pauli, and then within 3 weeks, Pauli has a reaction to it. He says, I understand what you're saying. If I look with my left eye, I see a particle. If I look with my right eye, I see a wave. If I open both eyes, I become crazy. And so there's something of that, what you will see today. We look with the left eye, right eye. It's not always clear we can open up both. Here's actually a lovely quote of André Weil, famous mathematician, long-time institute faculty member, where he says, these obscure analogies, blurred reflections of one theory or another, an illusion that two things are the same, but perhaps they're not. And it's in fact these kind of very intuitive feelings that two worlds have to be connected that are driving mathematics in a very, very powerful way. It's, by the way, a wonderful property that in one of the most rigorous fields, intellectual fields, mathematics, there's kind of art forms to express kind of uncertain and ambiguous relations. So there's the conjecture, there's the program. Somehow two things have to do something together, but we don't know exactly how. Well, an important element in going forward is, in some sense, our aesthetic feelings. So the Institute for Advanced Study was created in 1930, and the founding director, the first thing he did was not make a building or recruit faculty, but ask an artist to design a seal and devise a motto. And the motto he found was truth and beauty. And there have been many reflections about the nature of truth and beauty. Both are very important in mathematics. I would even say that mathematicians and perhaps scientists are one of the few who talk about beauty with any sense of irony. Like in art, you can no longer describe a painting as beautiful. It has to be interesting or whatever. But mathematical equations are just still beautiful. And this is a wonderful line by another institute professor, Herman Weil, who was asked, how do you manage with truth and beauty? He said, always try to combine the two. But if I had to make a choice, I usually chose the beautiful. Here's the famous physicist, Paul Dirac, who said that it's in physics more important for the equation to be beautiful than to fit experiment. There is actually an opposite point of view that I want to present to tonight. And actually, I love this quote by John Wheeler, the physicist, who said, every law of physics pushed to the extreme will be found to be statistical and approximate, not mathematically perfect and precise. He was making exactly the opposite point. And his point of view is that by being approximate, there might be still some kind of flexibility that allows the law, the physical law, to survive. Here's another famous quote by Francis Crick, from Crick and Watson fame. Any theory that accounts for all the facts is wrong because some of the facts are always wrong. So let me just say one word about this whole notion of truth and beauty in science. And so I would say there are two opposite points of view, where you find the true, deepest beauty in the natural world. And this is roughly the point of view from particle physicists or condensed matter physicists. So particle physicists would say, well, we look at this kind of garbage, which is like everyday life with all its complexities. And if you reduce to the elementary particles, you find these incredibly beautiful equations. So ultimately, beauty is found at the smallest distances. Condensed matter physicists would say exactly the opposite. If you have a glass of water, you can describe it as the motion of 10 to the 24 molecules. But you would miss the laws of hydrodynamics. You would miss the laws of thermodynamics. These laws are not present in the microscopic description. They emerge in the macroscopic description. So great beauty is found at the very other end, at the largest structures that we find in science. I imagine we'll make the point tonight that there's a similar kind of distinction in the framework, the language that we use to describe the large and the small. The large is the realm of gravity. We use Einstein's theory of relativity, of space and time and curvature and gravitational forces. The world of the very small is the world of quantum mechanics. Very counterintuitive. A world of operators and uncertainty, much more kind of an algebraic world. And you can say that the reflection in mathematics are the two ways of thinking about math. The geometrical way, which I would say is the visual, the right brain way of looking at math, sketching, walking around your object, and the much more algorithmic, algebraic way of doing math. Like a computer code, you do steps. I note in math education, these are two completely different ways to learn the field. And perhaps some of you, if I want to give you direction, some of you would love to see a map. Others would like to see an algorithm, left, left, right, left. And you might be either more literary or more visual person. And both these ideas are around. In fact, what I will try to explain to you that in some sense, in mathematics, physics is giving us way to go from geometrical objects to algebraic objects. So shapes and going to numbers. And in fact, there will also be some way to go the other way around. We can also go from algebra and geometry will appear. So if you will have a discussion, what is more fundamental, the conclusion tonight is that there isn't really this kind of a perfect symmetry. And in some sense, we have to find the synthesis from these 2 points of view, the macro and the microcosm and the macrocosm, or if you will, the algebra or geometric way of looking at the world. Now, to begin, I want to give the mathematicians a kind of a little kind of crash course in physics. So this is roughly the ABC. So I would say there are various stages in the evolution of physics. The first one, I would say, is the classical world. So in classical mechanics, you want to go from A to B. And the question is, what is the way you go? And typically there's some preferred path. It would be the minimum of some action. You find some geodesic in a space or the solution of a differential equation. And of course, this is classical mechanics. It was born in the 17th century, and it led to terrific applications in math. As I said, to calculus, to analytic geometry, to dynamical systems. And then in the 20th century, we got quantum mechanics. And in quantum mechanics, it's not about the question how you go from A to B. In some sense, in quantum mechanics, all possible paths are being explored. Quantum mechanics has this phenomenal, deep concept of a sum over histories, that you sum about all the possibilities, weighting by the action of the specific path. And in some sense, that leads to a completely different realm in mathematics. Many topics that were kind of discovered in the 20th century. The third level would be quantum field theory. In quantum field theory, you start in A, and you can end up in both B and C. Particles can be created and annihilated, as they have been done in particle accelerators. So it's much more about summing over graphs, the famous Feynman graphs. And actually, those areas in mathematics are relatively recent. They are being developed over the last few decades and are extremely fruitful in mathematical results. Another phase would be string theory. In string theory, we'll meet it very soon, instead of thinking of points, we think of loops. And instead of thinking of summing over graphs, we sum over surfaces. And again, this gave rise to a whole different set of mathematical subjects that are very, very new. And I would say we're still kind of scratching the surface of that mathematical area. And kind of the highest level, and we'll end up my lecture with this, is quantum gravity. In quantum gravity, space itself becomes a quantum mechanical object. So we just celebrated this year, actually last Tuesday, the Nobel Prize to gravitational waves, ripples in space and time, a discovery exactly 100 years after Einstein first proposed this. So space can ripple and can move. And we think that at the smallest distances, the incredibly small distance of Planck length, space itself will become a quantum mechanical object. That is to say, at the smallest distances, it's not even clear where a point is. So geometry kind of disappears. It gets replaced by something completely different. And then the question is, what kind of mathematical language is able to capture these very foreign ideas? So my prediction from physics is that the classical field of geometry, as we study in mathematics, has to be altered. There must be some way in which we can generalize geometry to something that really uses the insights of quantum mechanics. And as I will show you, there's two steps. We can use string theory. There's some wonderful examples of generalized geometries, stringy geometry. But in the end, we need something like a quantum geometry that is really an emergent quantity. So you take a picture and zoom in and more in, and you see the individual pixels. In physics, in some sense, we're looking for the atoms of space and time. Now, I want to start the story with the classical story and then slowly move to these kind of various stages of this intellectual development that's been happening in the last 50 years. And I want to start with particles. And actually, one of my favorite stories, which is a question that, some of you might not have asked. You learn about the properties of particles. But, these particles are all identical. If you have two electrons, there's no way in which one is a little bit heavier than the other. So if you think about it, it's quite remarkable that nature has a facility to produce particles that are exactly the same property. It's something that modern physics is able to explain. And the origin of idea was actually a telephone conversation between John Wheeler and Richard Feynman. Feynman was at that point a graduate student in physics in Princeton. And Wheeler calls him up in the middle of the night. And he asks, do you know why all electrons are the same? Why they have exactly the same property? And his line is, well, because there's only one electron in the whole universe. In general, a joke, if your thesis advisor calls you in the middle of the night with a crazy idea, but in fact, it's in some sense this idea that led to the really big breakthroughs of Feynman. And this was Wheeler's idea. So this is space-time. So you think of this as slices of space moving upwards in time. Here's an electron. And Wheeler had the point, well, suppose the electron could go not only up in time, but back in time. Now, if I could time travel, I could reappear here as an exact copy of myself. So there would be two Roberts, and they would be exactly identical. So if instead of going up and down, this electron is able to weave a big knot in space-time. And you think of this as slices of space, so like pictures that you take at certain moments in time. There would be one electron in the initial, but if you slice it in the middle, you see many electrons, in fact anti-electrons. And they would all be exactly the same because it's the same particle. So this was his idea. And Feynman basically forgot about it, and then in the 1940s, when he was kind of bored with his other physics, he started to come back to this idea. And I love this page from his notebook, because you can see him here literally sending these electrons back in time and seeing how do the rules of quantum field theory behave if you try to do this. And it's actually worked out magically. So this actually started to work. And now we know of these objects as Feynman diagrams. And they are allowed, in this formalism, particles are allowed to go back in time. And Feynman had this vision, at that point. Most people were doing, very difficult calculations. Perhaps you can just do drawings. And he had this image that perhaps at some point physics books would be full of drawings. Wouldn't it be that lovely? But of course, now they are. In fact, they are so popular that my favorite story is about this van. So this van drove around in L.A., and there's a story that a physics student saw the van, and there was a lady driving the van, and he stops her at the traffic light, and he goes up to her and said, Mrs., do you know that these symbols on your van are actually called Feynman diagrams, and we use them in physics every time? And she said, yes, I know, I'm Mrs. Feynman. And here's the Feynman family with the van, I think. Very 1960s, I would say. And of course, it's incredibly successful. In fact, the role of mathematics in this was not always clear. In the 1960s, actually, at some point, physicists were giving up this idea that these Feynman diagrams were still able to capture everything. And at that point, we had kind of a black box model of physics, where you see physics, something coming in and coming out, but it's very difficult to connect the two concepts. And actually, Freeman Dyson famously gave a lecture in 1972 where he said, basically he declared the marriage between physics and mathematics to be divorced and broken up. Because at that point, physicists and mathematicians weren't talking to each other. There's a famous letter that Feynman is invited to a math conference, and he writes back, I think, a one-line answer. I'm not sure why. I've seen no reason why I should attend a math conference. But very soon thereafter, I would like to say the black box was opened, and inside was a very tiny formula. So this is the formula, used very clever mathematical symbols, that describes the particle, the standard model of elementary particle physics. And the symbols that are used there, and the mathematical language that's being used, is incredibly natural and elegant and beautiful, I would say, from a perspective of geometry and mathematics. In fact, in some sense, the unifying theme connecting modern particle physics is symmetry and in all its realizations. Going back to original ideas again of Hermann Weyl. In fact, talking about dictionaries, this is a famous paper from the 1970s. It was actually the outcome of a seminar at Stony Brook between the Nobel Prize winner Xian Yang and the mathematician Jim Simons, and they were just comparing notes, and they noticed that, wait a moment, all the objects I'm studying, you have too, alone you give them different names. And that was an example, I think, where in some sense kind of a Rosetta Stone was discovered. And nowadays, symmetry, I think, is really our guiding principle. So this is my kind of a cartoon version of introduce it. So for instance, if you think about the theory of quarks, they have an internal label, so you can think of them as having a little, hope you admire my PowerPoint skills here, there's a little kind of arrow that moves around in an abstract three-dimensional space, and that symmetry is not only present at one particular point, it's like present at all possible points. In fact, there's not this kind of a Stalinist point of view, there's a much more kind of a democratic point of view, where in some sense these arrows are able to wiggle at each point in space and time. So there's a huge symmetry group underlying our particle physics, and in some way you can think of modern fields as kind of waves in these kind of little arrows. And if you bring this whole concept into the language of quantum theory and Feynman diagrams, then these become particles, colored particles, and in fact the particles that mediate these forces in the gate theory, you can think of them as a very natural way as kind of matrices. They are labeled by two kind of colors if you want to, say, turn a red quark into a green quark. Now the rules of quantum theory are even more bizarre because, as I said, as Feynman was expressing, particles can kind of interact, they can be decayed, but they can go back and forward and backward in time. So there are these so-called virtual particles that kind of exist for a very brief time. My favorite joke is that, in the Netherlands, so we have a rule of this that basically anything you do fast enough before it's being observed is fine. And this is somehow a very natural way to describe quantum mechanics, because these particles live for a very brief time. In fact, the kind of ultimate process in quantum theory is this process, which you can either think of a particle and antiparticle being created out of nothing and then decaying again, or, taking Wheeler's point of view, a particle going up and down in time in an endless loop. So these diagrams exist. In fact, they exist right as we speak. Empty space, according to modern quantum field theory, is filled with these so-called vacuum fluctuations. So again, this is my animated, my kind of visualization of the vacuum, where you have a kind of a boiling pot of particles being created and annihilated at a very constant rate. And so this is, again, an underlying principle of quantum theory. As Murray Gell-Mann said, that everything that is allowed is obligatory in quantum mechanics. Anything that can happen will happen, perhaps with a very small probability, but it does. And I think this is the first point I want to emphasize, that the quantum theory has a very different point of view on life. It's not looking at one specific instance. It's looking at all instances at the same time. And this fit very much the modern view of mathematics. The modern view of mathematics, you do not consider one particular object, but you always consider the kind of the universe of all possible objects in that category. So it could be whether it's sets or symmetry groups or whatever. And so we always think about the whole universe and the relations among the inhabitants of that universe. So from that point of view, quantum theory is a very natural way to look at everything at the same time and kind of bring some kind of order in that particular universe. And it has been very powerful in this way. So one of the earliest successes of the application of quantum theory in pure math actually appeared in knot theory, typically a subject that happened in the 1980s and 90s. So what is a knot? A knot is a curve in three-dimensional space that closed on itself. And one of the problems in mathematics was to kind of give a list of all possible knots. So you could imagine it's like a universe, there's a book of knots with an infinite number of pages, where all these different knots are, and how do you distinguish them? And the way this problem was solved by kind of seeing this in the language of Feynman diagrams. So you can think of a knot as a trajectory of a particle that goes up and down in space. In this case, you have to make a space-time of 2 space and 1 time direction. So you have to make something with 3, not 4 dimensions. And for each of these diagrams, the laws of physics will give you a certain number, namely the probability amplitude that this actually will happen. So in fact, you can do even more precisely. You can think of this as, say, a quark going around in space, one of these virtual diagrams. And it can interact by kind of shooting gluons as ordinary particle models do. And for each of these kind of Feynman diagrams, you will get a specific number that turned out to be incredibly powerful in solving the mathematical issue. So in some sense, the knot theory was crying out to be reinterpreted as a theory of particles moving in space-time. My second example is an example from a kind of esoteric subject that's related to string theory that was very fashionable in the 19th century and then had this incredible revival in recent years. And it's called Enumerative geometry. And it's studying certain spaces. The most famous is the so-called Quintic. It's called a Quintic because it's a function of 5 variables that all are raised to the 5th power. If you think about this, these are 5 complex variables. You have 1 equation, so you have 4 left. And then there is an obvious scaling relation get out. Turns out to be a space of 3 complex dimensions. And one thing that mathematicians were interested in the old days, and still are, is counting objects. And it turns out it's an interesting question to count the number of curves you can draw on this 3-dimensional space. So drawing a curve means that you have the 5 variables. Each of them are polynomials in some extra variable z, say polynomials of degree d. And then you can study these questions, so how many of these curves are there in degree 1, in degree 2, in degree 3, etc. And you can imagine that these problems soon become very, very complicated. The case of degree 1, so the number of lines that you can draw on that space, is a classical result from the 19th century. So I think every real algebraic geometer will know there are 2,875 lines on the Quintic. Then to go to the next level, so conics, so degree 2 curves, there's already a huge number, 609,000. And this was computed in the 1980s. And the next case, there's an interesting story to it. The story is it was computed by mathematicians because physicists wanted to know the number. So they asked, can you compute it? It was a very complicated calculation, a lot of computer algorithms involved. And they came out with a number, not this number. And then the physicist said, are you sure it's the right number? Didn't you make a mistake? And they went back, and indeed, the mathematicians found that there was a mistake. And they got this number. So, but then, of course, how did you know we made a mistake? And then the physicist said, well, you know, we have all the numbers. And so it's hard to bring home the shock when this first happened, because it's like this has become exponentially difficult with each step. So what was going on? How were physicists able to do all the calculations at once? And of course, the answer is again quantum theory. Using the sum of histories. In this case, thinking of counting curves as the movement of a string that takes all different shapes in this particular space. And what quantum mechanics will do, it will calculate this amplitude, this probability, by summing over all histories. And so there's this kind of nice function, and the coefficients in the function were the numbers that you want to compute. So that was the first insight, that these numbers, you should not look at them individually, you should see them all at the same time. But there was a second thing that was happened, which was like very, very much a surprise. Physicists were interested in these spaces in string theory because they used to wrap up internal dimensions. I won't go into this, but so they wanted to know what kind of these kind of spaces exist, these so-called Calabi-Yau manifolds. In fact, in physics, the choice of such a manifold would lead to a particular particle model. So part of understanding the physics is understanding all the models, and so also understanding all the spaces. And originally, they made a map. So what physicists do, they make a plot. These spaces were characterized by 2 numbers, and so you could make this kind of scatter plot. And looking at the plot, they say, well, there's a symmetry there. It looks like for every space X, there is like another space on the other side that's very different but it seemed to share some properties. And this was a major discovery. It's called mirror symmetry because there's like a reflection that goes from the left to the right. And it turns out that with these two spaces, which were really couldn't be more different, seen as real spaces, through the eyes of quantum theory, they certainly became the same. It turns out that the quantum mechanical properties of the two spaces were identical. And so it turns out that on the one hand, you were doing these very complicated calculations. These were the numbers that the mathematician trying to prove one by one. The same calculation on the other space, the mirror space, turned out to be a very simple calculation, a classical calculation that people could do. So certainly by using the Rosetta Stone and going to the other side, using the other language, a very difficult problem was actually solvable. So this was a great success. In fact, this is the beginning of a wonderful program that led to very terrific results. And so we could declare victory, but now there's a kind of a thing that's kind of unfortunate, which is that somehow physics and mathematics doesn't seem to commute. That is to say, these things have been proven, but the mathematical proofs didn't make the physical intuition precise. In fact, the mathematical proofs do not use the other side of the equation. They basically stay on one side and just prove the results. They just prove that the numbers are where they are. And so it's very difficult in some sense to... Physicists had hoped that mathematicians would somehow provide firm footing of their very intuitive and kind of shaky ideas. But it hasn't happened. So one important theme across this lecture is that, is it true that physical intuition might point you to certain equations, certain relations? I'm not quite sure whether the physical intuition is enough to finally make these proofs. And this is a particularly relevant for the third topic that I want to discuss, which is the realm of quantum geometry. So I think basically physicists are telling mathematicians this is only the beginning. You have to more thoroughly and deeply question what you mean by geometry and by algebra and really think of something very, very different. And the reason for this is that essentially what is, I would say, an existential crisis in physics. And it has to do with the really violent phenomena that we study in the cosmos. So I would say black holes and the Big Bang singularity in our cosmological evolution. So the remarkable thing is we have this very beautiful theory of Einstein's describing space and time in its curvature, but it has some kind of mistakes, or it has some kind of gaps, very important gaps, which are singularities. So if you think of the cosmic evolution, there are 2 points that we worry about. The Big Bang, which is the beginning of time, and in some sense, part where in some sense Einstein theory breaks down. And in a similar way, Einstein theory breaks down in places where time ends, that is inside black holes. Now, again, there's a great quote of John Wheeler about this. He said, and this is from the 1960s, the existence of space-time singularities presents an end to the principle of sufficient causation. What happened before the Big Bang, essentially? And so to the predictability gained by science. How could physics lead to a violation of itself? How could physics lead to no physics? And so that's one of the fundamental questions that modern physics is involved with. How could it be that our great theory has this kind of built-in deficiencies? And we feel that black holes are, in some sense, the way forward. Many of us feel that the black hole has the same kind of center stage now that the atom or the particle had 100 years ago. And that led to the birth of quantum mechanics, a great revolution in our thinking that, as I tried to indicate, also revolutionized our mathematical language. I think we are now at a stage where we need a further revolution of that kind. And black holes are interesting because I know, as it's said, they are very paradoxical subjects. On the one hand, they are the most simple object. It's just a hole in space. On the other hand, they're the most complex because it's the most efficient way to condense information. In physics, we think we have a way to calculate the information content of a black hole, and we think it's equal to the size of the horizon, so that's the area, kind of the no-go area that surrounds the space-time singularity, measured in these Planckian units, so in the bits of it. So we think roughly that is kind of the schematic view of 1 bit of information placed of each kind of square Planck length unit on the surface of this horizon. So black holes should kind of marry quantum mechanics and gravity in a very meaningful way. And again, black holes provide us a dictionary. It's another Rosetta Stone. It's a Rosetta Stone that which compares the laws of thermodynamics and the laws of general relativity, quantum gravity, in the presence of black holes. So as we said, there is a concept of entropy, the amount of information that you can store in a statistical mechanical system, as measured by the horizon of a black hole. We feel that the second law of thermodynamics, that entropy always increases, has an equivalent in black hole physics. If 2 black holes merge, that they create a black hole whose horizon is larger than the sum of the 2. And of course, with this recent LIGO discovery, we actually have physical evidence of this process, and indeed it kind of works, so to say. And finally, I think there is something like a temperature concept too in black holes, because there's a concept of Hawking radiation. Black holes, under the laws of quantum theory, are not strictly speaking black. They are some way to emit particles. So again, this is an example where there's seems to be an analogy. And this analogy could be more than an analogy. We are essentially looking for the equal sign that puts these 2 worlds together. Now, there are again, from string theory, some very interesting ideas, and so I want to share a few of these with you. The way to apparently forward to describe these black holes is using a technology using so-called branes, which are objects inside space where strings can end. So in string theory, there are, apart from the closed strings that I described before, there could also be open strings, little open lines that can be end on something, and that's what we call a brane. And these branes are terrific because the mathematical language that you need to describe them turns out to be the language of Yang-Mills theory, of gate theories, of matrices. So in some sense, again, we are given a gift, namely a mathematical framework that describes these objects. It looks very different from geometry. It's actually an algebraic framework. It's studying the same matrices that are responsible for the symmetries, for instance, in the standard model, the quarks that you saw. So here's my kind of cartoon version of what is kind of happening here. So you can think of this a little bit as follows. So think of these kind of branes. It's not an accurate description, but it's for a cartoon version it will suffice. Think a little bit at these branes at the horizon of the black hole. So in string theory, we'll have the kind of these closed strings. As I said, they should be responsible for the space, time, and its curvature. And then you can have these so-called open strings, and well, intuitively you can think of them as kind of little strings that have been falling halfway through the horizon. So they're kind of just sticking out and waving, help, help. And it's these kind of open strings on the surface of the horizon that are some capturing, that's a string theory cartoon version of capturing the information inside the black hole. In fact, here's my kind of animation that would kind of look like how Hawking radiation could look like. You can think of 2 of these open strings, meeting and touching and then, forming a closed string that kind of lifts off and is able to escape. So remarkable that, within the framework of string theory, there have been some very precise calculations, only very specific examples of these kind of quantum black holes. So we feel that we are at least pointing towards the right language to capture the singularities of space-time. Well, this was all kind of brought together by a really fascinating paper that somehow changed a lot of physics for the last 20 years. The paper by Juan Maldacena, who proposed something else. He said, there is actually another way to capture not only the black hole, but capture actually space-time itself in terms of a theory that in his language was kind of living on the boundary of space-time. So this is the famous ADS-CFT correspondence. And from a mathematical point of view, the statement's actually the following. It's saying, well, again, there is a Rosetta Stone. There are two languages that should be talking to each other. On the one is the language of gravity. So it's the language of space, time, and curvature, and gravitational waves, and black holes, and all you have. On the other hand, there's a theory of quantum gravity, of quantum mechanics, sorry, that's, it's somehow living on the boundary of that space, and should be entirely equivalent. So on the left-hand side, you wouldn't see anything like space-time curvature. You would typically have quantum mechanical effects. On the right-hand side, you would find these objects. You would find space, time, and curvature and everything. And what we have been doing in the last, say, 2 decades in physics is really constructing this dictionary and extending the left side and the right-hand side, and finding all these magical equations. Again, the equal sign is incredibly important here. In fact, this kind of idea of Clinton's principle, what do we exactly mean by is the equality here, is taking a lot of kind of mental energy in physics, because what do you mean exactly if these two are equal? Is the left-hand side defining the right-hand side? Or to which extent are both well-defined? Who is helping whom in this particular situation? But I think it's entirely fascinating because it's all pointing out to something very deep. It's pointing out something that, perhaps the ultimate physical laws that we're looking for are not at the, reductionism isn't somehow our guiding principle. We have to think in terms of the other kind of beauty, the emergent kind of beauty. Of course, for Einstein, in some sense, for him, the ultimate dream was to make the whole world out of geometry. I think he really thought geometry is such an essential way to look at nature that he felt it was not only the foundation, but in the end, everything should be created out of geometry. The later years in his life, he's spent a lot of time producing particles, in some sense as little knots in space and time. I think the modern point of view of physics is that geometry is not the ultimate foundation, but it's like a basement below that. You can go even deeper. And in some sense, this kind of quantum theories by themselves are perhaps a much more fundamental description of what nature is. And so that in some sense the space, time, and gravity, and perhaps also the objects moving in space-time aren't a fundamental description, but in some sense are emergent out of something more fundamental. That I think we honestly are lacking the mathematical language to find that. One thing which is interesting, there were two theories that Einstein thought the most beautiful. One was the laws of thermodynamics, and the other were his own laws of general relativity. And so, in fact, if this kind of analogy becomes an equality, it would be very satisfying, because they would, in some sense, be the same. Now, in mathematics, I would say, though, there are small hints of what the kind of language is that we need here. And I just want to end by giving a very tiny example of something which presents something of this kind of emergent geometry. And this example out of statistical analysis. So there's a famous field in mathematics that studies random matrices. So just, and in fact, its birth came in the study of nuclear spectra, where people were thinking, well, it's very difficult to exactly compute the spectrum of a specific system. Why not make a kind of a statistical ensemble? And thinking of, in some sense, a model where you have a random matrices with a certain distribution, a Gaussian distribution. Now, if you have such a matrix, it has eigenvalues, and these eigenvalues will be somewhere on the real line, so these are the eigenvalues of this particular matrix, and if your matrix will rank n, they are kind of distributed with a certain width. And what Wigner found, that if you make the matrix larger and larger and larger, these eigenvalues start to kind of cluster. In fact, they form a very natural kind of eigenvalue density. In fact, that has a very beautiful shape. That's the shape of a circle. So a very elementary geometrical object, the circle, is emerging by studying this system, which you can think of as a completely caricature quantum mechanical model that has a variable, namely the rank of the matrix. And if you increase the rank of the matrix, or you increase the complexity of the system, then you slowly approach this kind of a classical geometrical shape. Well, in fact, this is a very precise mathematical field, and you can do there are many other similar models, and indeed in this realm, you can find something which is a very nice example of emergent geometry. So if you study these statistical mechanical models, and you take the limit where essentially the rank or the number of particles becomes infinite, you see that the model is captured by very classical geometrical shapes. If you make n large but not infinite, you can do an 1/n approximation, and you can look also at these systems for finite n, and you find something which I think is a good example of what would be a quantum geometry. But I think we have to be honest that we're in some sense still lacking the right language. So my grand vision is that by studying many of these examples, like we have had before in the time of classical mechanics, that perhaps a new vocabulary will emerge. Something, perhaps even a new breed of mathematicians that feel at home in a natural way in quantum mechanics. Now, if you look at the system right now, we see there's all these wonderful examples. There's tons of exciting developments. There are many, many areas in mathematics that are involved, but it's not yet a complete picture. Reminds me of one of my, there are many jokes about mathematicians and physicists, and often they are at the cost of the mathematician, I'm afraid. But one of my favorites was actually told by Alan Kohn, the Fields medalist. And he said, well, it was the physicist, and he had a very big bag of dirty laundry. And he went into town, and he was looking to a place to do his laundry. And then suddenly he sees a shop, and it says laundromat. In fact, it not only says laundromat, it says restaurant and cafe and lots of other, hotel. And he comes in, and of course the shop is run by a mathematician. He says, can I do my laundry here? I said, no, unfortunately you cannot. I said, but I saw the sign. No, this is a shop that only sells signs. And, and sometimes that's some physicists feel that all these grand topics, but is there, can I do my laundry somewhere? But I would say there's another, perhaps a deeper philosophical point of view. As I said, in some sense, we have these different languages, and we are finding dictionaries. Dictionaries between algebra and geometry, between quantum theory and classical theory, between general relativity and quantum mechanics. And it's a little bit like ordinary natural languages. There are certain things you can say in English that I cannot say in Dutch, and vice versa. Perhaps it's like describing the Earth, not in terms of an atlas and maps. So you have various maps, and you have ways to go from one map to the other. So this could be, in the end, the way we have to describe the world, so to say. Of course, that's one point of view. But I think that the real intellectual challenge is to kind of find some kind of a unifying theme with all these examples and all these ideas. It would be incredibly powerful. It would be the language that would be helpful to capture the fundamental equations of physics. But also it would be a great unifier in mathematics itself. Because if one thing that we see that physics has been doing, quantum physics in particular, it has been kind of crisscrossing these various mathematical fields with kind of very little respect for the natural boundaries of these various topics. So if I want to end it with a dream that perhaps at some point there is somebody will find me a globe, and we have quantum mechanics, quantum mathematics as one specific subject. Thank you very much. Yes.
So, you mentioned atoms of space-time, and then you never really got back to it, but you sort of brought in black holes as maybe the equivalent of the atoms of quantum mechanics. I mean, is it inevitable that space-time or space or time is quantized and that there are quanta of space-time or space or time, and is that role filled somehow by black holes? Is that something like what you're saying? It's very confusing.
Well, I think you're quite right pointing out, I used kind of the concept of atom twice. I think the first point is that we do feel that, you know, the classical model of space as having kind of this infinite number of points. You know, you can zoom in endlessly to the smallest structure. There's no limit to it. That actually is an unphysical model because it's like strictly impossible to measure space differences between space and time. If you with experiments, at some point you will have to put so much energy in such a small area that actually the laws of physics will prevent you from doing this. So I think we're in general agreement that, you know, there's not the classical mathematical model of space, Euclidean space, is not the right one to describe physical space because, you know, there is some kind of natural cutoff. So when I'm talking about atoms of space, I'm not thinking of literally that there are little blobs or something. So the analogy of the pixels in a computer screen is not the right one. I think it's a better analogy would be the zeros and ones that encode the picture as a computer file. So I think we do feel that there's like a finite amount of information that can be stored in a certain area of space. And a black hole is one way to capture the amount. So you can think of you create a little hole in space and you ask, you know, how much information is there? And the black hole will compute for you the amount of information. Of course, if you have classical space, you could put an infinite amount of information because you could create, you know, units that are infinitesimally small. So in that sense, I think the two concepts are connected. Perhaps you can hand the mic or something. Yeah.
Can you comment on two recent developments, one that you call amplitudology and the other, the Eric Verlinde's work on volume law and its relation to dark matter?
Okay, let's start with the first. So one part of this struggle, I think, to find the right mathematical framework is that even in the physical models that we use, like quantum field theory, I would say that there's kind of general agreement that although we all love the Feynman diagrams and the gauge fields and all of that, that's only a partial description of these physical models because in some sense they have a much richer structure and deeper symmetries. So the amplituhedron and this amplitudology is another approach where you say, well, it's almost going back to the black box that I started with. You know, I joked that the black box could be opened and the formula of the standard model was there. But I mean, perhaps this kind of abstract point of view in saying what is a physical theory, it's a machine that computes certain quantities for us. So there's an input, there's an output, there are certain consistency conditions. That idea totally resurfaced. And so in some sense, you know, physics is now trying to kind of map out what is the space of possible physical theories. And so this is one particular approach to it. It's a very top-down approach. And it's, you know, it's very exciting to see to which extent we can push that approach. And whether, I mean, perhaps it's almost like understanding physics without understanding physics, because you just describe all the objects, but you literally are not able to open them up. We'll see. The second one, I think, you know, Eric Verlinde's work, I think, you know, he's, in some sense, intuitively, I feel what he's going to say, is trying to say, and I think, you know, he's making the point that many of us make, that space and time should be emergent quantities. The relation with dark matter is very tempting, but I think, you know, I don't really understand the details of his arguments. Yeah. Would be terrific in some sense if something like that would be true, but I'm not yet there that I would claim I understand.
I think he got first.
Yes, there?
Oh, I'm?
Yeah.
Okay. In the slide where you compare the quantum theory and gravity theory, I just noticed that you use an illustration by M.C. Escher on the gravity side. So just want to know if there's any meaning behind this detail.
Sorry, which equation? Sorry, I missed that.
The slide where you compare the quantum with gravity.
Yes.
Yeah, I think you use an art by MC Escher.
Oh, okay. So that's Why was the picture of Escher there? Because it's because the space that particular is the so-called anti-de Sitter space, which is negatively curved space. So this particular, the original application of this idea was in space-times that essentially have a boundary. So they are negatively curved, and so that's why you get the Escher picture where you see more and more objects on the boundary. So one of the issues in studying these kind of dictionaries is exactly, what kind of spaces can you have? Can you produce in that way? And so I think this is something, it's actively investigated, whether you can have, for instance, de Sitter spaces, which are the spaces that actually are relevant for our cosmology, and what would be the appropriate object on the left-hand side. So again, I think it's a good example of these kind of deep identities that we also see in math. So there's some equal signs, certain things are connected, but on both worlds there are many models yet where we don't have the specific connection.
So please excuse me if this question is completely missing the point, but you described these concepts of particles and antiparticles being created by moving forward and backward in time.
Yeah.
And so two questions arise from that. The first is, can that model explain, does it correlate with why there is more matter than antimatter
and actually
in the universe? Was it sort of inconsistent with that idea?
Exactly.
And then the other question is, when a particle and an antiparticle collide, they destroy each other with an amount of, there's a release of energy which is more than the energy of just the particle.
Yes.
So where does that energy come from if it's a particle that's moving backwards in time? It seems like creating energy out of nowhere.
So your first question was apparently exactly the answer that Feynman gave when Wheeler called them up. So well, why aren't there equal number of particles and antiparticles? And of course, this is why it's wrong. There's not only one electron in the universe. There are many. I'm composed of many. You are. So there's a net amount of electrons. It's more about, so you think, so the right way was, if you think of the movement of a single electron, actually even the ones in our atoms, they can make these kind of wiggle movements, and they do. Actually, you can see this, in physical experiments. And what it does, it creates a cloud of particles and antiparticles around a physical particle. So it's not true that there's one electron, but still this idea of going back in time is part of physics. The second question is that these particles are not real particles, they're so-called virtual particles. They're particles that are used in our calculations. So in this process where you create a particle and antiparticle, you don't violate the conservation of energy. So one particle has positive energy, the other one has negative. The one with negative is so therefore not a physical particle. So if they annihilate and give zero energy. So again, these are, you can think of them more as calculational schemes. They're not observable particles. Okay. Although the indirect effect of these diagrams, these Feynman diagrams, we can measure.
Okay. So I did have the same response as Richard Feynman.
Yes, yes. Now apply it and earn a Nobel Prize. That's yes. Step one, reproduce step one.
Yeah.
Yes.
So what happens to axiomatization in this quantum mathematics? Like, so do we have an axiomatic basis? Like, is it set theory, category theory? Like, so what happens to axiomatization? Like,
that's the golden question. What are the axioms? What is the natural way to build this? I don't know. I think But so one thing I would love to see is a generalization of the concept of a geometrical space that in some sense includes these kind of quantum corrections in a natural way. It's not even clear, I think, here which has to go. It's not clear that we have to adapt to a quantum point of view on everything, because, as I said, the quantum theories that we know are themselves limited, and our own understanding of the theories are wrong. So I think we're looking kind of a concept that in some sense kind of unify these two concepts, and yeah.
So, but there is no current axiomatic basis like bottom-up of this quantum mechanics?
There are certain axiomatic ways to approach quantum theory, but I think in general they have been kind of failing. And so the question just got from kind of top-down approach, which is like looking at this kind of bootstrap or amplitude, is some way to have other information. It's very difficult to give an axiomatic definition of these quantum systems because easily your axioms include lots of stuff that you don't want to have. Or they exclude the interesting cases. So I think if we would know the right axioms, we would be in a great position. But I think perhaps that's what we're aiming for. And so the attempts that the physicists do is kind of mapping out a landscape, which is a very fragmented landscape. It has many kind of islands and mountain ranges and everything, and lots of surprise new areas that we didn't. It's all about understanding, in some sense, what is this kind of universe of physical theories that we're trying to study. Yeah. Yes.
Hi, Professor. Professor Dijkgraaf. Thank you very much for your talk. So my question is not going to be very well formulated, but it's generally regarding your comment on mathematical rigor versus physical intuition.
Yes.
So in your few examples, the calculation in Gromov-Witten theory
yes.
was very precise, and you said there was a mathematical proof that I can actually show you that this
yes.
works. However, on the side of, for example, the ADS-CFT correspondence that you mentioned, I think the mathematical community or the physical community don't have an agreement on how well this
yes.
theory is, or this correspondence is really established. And I've heard a lot of debates personally about the subject. So I'm just wondering if you have any comment on that as to how should physical intuition work well with mathematical rigor, and to what extent should physicists care about mathematical rigor without satisfying, say, their productivity and imagination on the physical side in generating ideas? So,
well,
if that's the case at all.
But these are discussions for over drinks, I think. But I think the one way I see it is that so the physics, we have these very kind of intuitive but very grand claims of what the two worlds should be that we unify. What has happened often is that you take these grand visions and then you condense them in a very specific mathematical equation that should be the consequence of that grand framework. And I think it's the great progress that we made in mathematical proof is proving some of these consequences. So I think even, for instance, in ADS-CFT, there are some specific cases where this boils down to a certain identity. There's a certain modular form and it can be expanded. I worked on this this fairy series, and there's like an identification. And so there are some cases where there is, I would say, often I frame it as follows. You had Plato's cave, where there are these mathematical deep truths and we could only see the reflections. I think this is something like the opposite, in the sense there's like these deep insights in physics, which are very hard to access. What we see is the projections in terms of concrete mathematical conjectures that then can be proven or not. And I think it's a good first step. But the physics, I mean, they're wonderful results, and people have been celebrating them. But now for physicists, I think we really want to have a conceptual understanding why this is true. And I think we feel this is only true the moment you really analyze the underlying beast, so to say, which is the physical system. If you understand that system, then this equality, A equals B, will be obvious. But now it's just a lot of hard work. So in that sense, it's I think for physicists, I think this intuition is more than just a way to get interesting mathematical results. It's actually a deep question that we want to answer, because it will point us to the nature of the object, of reality perhaps. So I think the role of these mathematical equations is that it sharpens the physical thinking. And I think it has. And another really remarkable development is that mathematicians have taken these ideas and generalized them, sometimes in a very spectacular way, which is kind of fascinating. So in some sense, a little bit like a tennis game. So perhaps in certain cases, the service was the physicist, but then mathematicians return the ball, and that by generalizing some of these concepts in ways that the physicists are now scrambling to find whether their intuition can kind of cope with these next steps.
Hi. What is the source of the almost perfect connection between mathematics and physics? And can the universe really be described purely mathematically?
Okay, that's another. I think we're getting to the end of the discussion session. I think. Well, I can just answer with some further questions because there's a huge debate about this. So, of course, it's a great gift that we have been able to capture so much of physics by mathematical equations. And there's a deep debate whether this is a reflection of the nature of reality, or it's a case if our brain is only able to capture those things and understand those things that we can describe in mathematical language. So a large part of it we might just totally be unaware of. My own personal point of view is that actually going back, I would subscribe what Galileo and others said, that mathematics is probably the right language to capture nature. However, as I tried to indicate, it's an evolving language. And like also natural language, it grows, there are new words, new concepts. So I think in its present state, it only captures a small part of reality. But it has been a terrific gift, and perhaps that's a good closing line, that mathematics has been evolving whenever it interacted with other fields of science, yet keeping its unity. That's the remarkable thing, that in some sense it has never really turned to something else. It just has expanded, became a more richer language with richer grammar, richer subjects, richer words, so to say. And I think, I think the deep belief of many mathematicians that this will continue, whether it's interactions with quantum theory or any other field, that in the end mathematics will able to kind of turn out to be the right language to capture it.
Yeah.
Yes. Okay. Well, last question.
Okay.
Yes.
Sorry. So something I found interesting that you said was black holes are the most efficient way of storing information.
Yes.
So I was thinking, if a black hole can store information, is there any way for that information to be read?
That's a very good question. There's some great experts here in the room that can talk about it. I think it would go too far too, but it's. Let me just say that that one thing that has happened in the last couple of years is that the whole field of quantum information, and as it's being used, very practical applications in designing computers or quantum computers, in some sense turned out to be again a subject that's very relevant for studying all of this. So I would say it's again a certain area of science, of mathematics, being brought into the fold. And it led to some, again, remarkable equations. I'm not sure whether this is the ultimate way to understand reality, but it's certainly part of it. So these things are actively discussed.
Well, let's take, you want to say something really? Okay.
Yeah.
He has to get the plane, he's taking the red eye. Should I go? Okay, fine.
Talk to Professor Suskan. He will give you all the answers.
Robert.
Yes.
It seems to me mathematics enters in at least two different ways.
Yes.
One way is just very often the very, very simple principles. Take Newton. Newton had just a couple of sentences that define basic Newtonian physics.
Yes.
All of it. And then there's all the mathematics which comes out from solving them.
Yes.
And that mathematics can often be very subtle, very complicated, elliptic integrals, and all sorts of stuff.
Right.
How do you know which is which? How the Gaussian flows, do they have to do with the fundamental principles, or do they have to do with the very complicated solutions of some very simple?
Yeah, you make a terrific point, and I would say the best example is number theory, right? So it's very easy to define numbers, but then number theory is this incredibly rich field, where almost any problem is unsolvable, and there are very, very deep themes. I think actually we are confused at this point, and I think somehow the two ways, the kind of reductionist and emergent point of view is actually might be even confusing these 2 points of view. So I would say at this point we have no idea what the axioms are, the laws that Newton posed with very, very, very simple math, and what are the applications, what are the technology. I personally feel we are in the technological point of view. I think we are solving equations, but we haven't yet discovered the laws themselves. I think that would be my guess. So we sometimes work backwards, I think. We develop all these very refined tools to analyze solutions, but we haven't really discovered solutions to what equation. Yes.
Knowing elliptic integrals and not knowing Newton's law.
Exactly, yes. Well, you could be a grandmaster in elliptic integrals in the 19th century, right? So,
Okay, with that,
okay, thank you.